Good afternoon, everyone. Today, we're going to introduce and satisfy an exponentially expanding dough conundrum. The problem is as follows. Brazil ought to prepare a brand new batch of dough pastures for her business using yeast to expand and increase the mass of dough. Per hour, the yeast naturally increases the mass of the dough exponentially by half. In order to match the standards per batch, the mass of the dough should be more than or equal to 650 grams but not higher than 950 grams to avoid late batches.
If she starts with 250 grams of dough, how long can she wait for it to achieve the preferable mass? What is the least time possible for her to achieve the preferred mass? What is the most time she could wait before the dough turns too light? If in a hurry, how could she only let the dough rest for 30 minutes? Can she leave the dough for 90 minutes? How about 3 hours?
Let's dissect the problem into four parts: the given, what is asked, the solution, and satisfying what are asked. First part, the given. Highlighted in yellow are the facts of importance. Firstly, per hour, the yeast naturally increases the mass of the dough exponentially by half, meaning we can deduce that for a given time t, given a mass, the dough increases exponentially by one half, by which can infer that the problem tackles exponential growth, specifically natural growth. Examining further, the problem shows the restrictions or the limitations of the expansion of the dough, specifically more than or equal to 650 grams, but not higher than 950 grams. Notice that in the second limit, 950 grams is considered acceptable. Thus, the mass of the resulting dough should be more than or equal to 650 and less than or equal to 950. The last statement too specifies the initial mass of 250 grams. So all in all, the following are the compiled data. The problem tackles a problem regarding exponential growth, specifically natural growth. Therefore, we should use Euler's number E. The rate of growth per hour T is one half, with limits of the mass being more than or equal to 650 and the mass being less than or equal to 950, and an initial mass of 250 grams.
Moving forward, we are going to construct the formula using our gathered data. As we recall, the formula for natural growth is the initial mass multiplied by the constant Euler's number raised to the product of the constant rate of growth and time. Plugging in the values, we get the following. Function d is equal to 250 grams times e raised to the product of the rate of growth, 1/2, and the independent variable t, time. Implementing the limits show us the following equation. Function d, which is 250 times e raised to 1/2 times t, should be more than or equal to 650 and less than or equal to 950.
Moving on, tackling the ask, we are seeking to find the values for t that would satisfy the given equation, where t represents the possible waiting time to allow the mass of the dough to be equal to or higher than 650, and lower than or equal 950 given the initial mass of 250 grams, and the natural growth rate of 1/2. Seeing the compound inequality, we must first separate it into two distinct inequalities, namely 650 more than or equal to d, the function for our dough mass, and d should be lesser than or equal to 950, after which the intersection of the two acquired solution sets will provide us with the answer.
Moving on to the solution. For our first inequality, 650 being less than or equal to 250 times e raised to 1/2 over t, we should first change the inequality symbol into an equal sign. Then, in order to isolate the term in which the variable t is situated, we are going to divide both sides by 250. which will result into 13 over 5 is equal to e raised to 0.5 or equal to 1/2 times t. Notice that the variable is situated in the exponent of the term. Therefore, we need to use logarithms. We find the logarithms of both sides. Log of the 13 over 5 is equal to the log of e raised to 0.5 times t. Notice that in the argument, there is still an exponent visible. Therefore, using the power rule of logarithms, we need to transpose such exponent in front of the logarithm. Therefore, we will yield log of 13 over 5 is equal to 0.5t times the log of e. To isolate the variable 0.5t, we need to divide both sides by the log of e. This will result into 0.5t is equal to the log of 13 over 5 divided by the log of e. Finding the values of such logarithms using a scientific calculator, we arrive at the following values. 0.5t is equal to 0.41497 over 0.43429. Solving for such operation, we derive at the value of 0.9551. Then, in order to find the real value of t, we are going to divide both sides by 0.5, which will result into t being more than or equal to 1.91 hours. Solving for the second inequality, we will do the same, so you can do it, JK. First, we need to exchange the inequality sign into an equal sign. Isolate the term in which the variable is situated, so we need to divide both sides by 250. This will yield 19 over 5 equals to e raised to 0.5t. Because the variable is situated in the exponent, we're going to use logarithms. The logarithm, therefore, of 19 over 5 is equal to the logarithm of e raised to 0.5 times t. Seeing the exponent in the argument of the logarithm, we need to be reminded of the power rule. Therefore, we need to transpose 0.5t, which is the exponent of the argument of the logarithm in front of it. Therefore, log of 19 over 5 is equal to 0.5t times the logarithm of e. Dividing both sides by the log of e to isolate 0.5t, this will result into 0.5t is equal to the logarithm of 19 divided by 5 divided by the logarithm of e. Finding the values of such logarithms using a scientific calculator for convenience will yield us these values. 0.5t is equal to 0.57978 divided by 0.43429. Doing the operations, t would be equal to 1.335 divided by 0.5. 0.5 will need to be divided in order to isolate the variable t in which 0.5 previously was multiplied upon. Therefore, t would be less than or equal to 2.67 hours. The intersection of t being more than or equal to 1.91 and t being less than or equal to 2.67 will lead us to t being more than or equal to 1.91 and less than or equal to 2.67 hours, which looks the same but is more elegant. Expressed visually, where the blue graph shows the exponential function and the red graph or the second graph showing the logarithmic function of the dose expansion over time, in which I should note that the x values of such graphs are scaled by 10 for clarity. The yellow area of the graph shows all the possible length of time in which Pretzel can wait to satisfy the limits of her standards. Therefore, the solution set for the function g over t being more than or equal to 650 and less than or equal to 950, t are all real numbers such that t is more than or equal to 1.91 and less than or equal to 2.67, which narrow down to the value of being 1.91 and 2.67 hours. All the solution in this set is these numbers included and those in between them. Therefore, Pretzel can wait between 1.91 to 2.67 hours for the dough to be in her preferred standard.
Lastly, we are going to satisfy the imposed problem at the start of this conundrum. Problem A, how long can she wait for it to achieve the preferable mass?
Well, pretzel can wait between 1.91 to 2.67 hours for the dough to be in the preferred standard.
Problem B, what is the least time possible for her to achieve the preferred mass?
A minimum of 1.91 hours is needed to achieve the preferred mass.
Problem C, what is the most time she could wait before the dough turns to crumbly?
At maximum, she can wait for 2.67 hours before the bread turns too light.
Problem D, if in a hurry, could she only let the dough rest for 30 minutes?
Unfortunately, no. She needs to wait for at least 1.91 hours and at maximum 2.67 hours.
Problem E, can she leave the dough for 90 minutes?
Unfortunately, not. 90 minutes translates to 1.5 hours, and she needs to wait for at least 1.91 hours and at maximum 2.67 hours.
And lastly, problem F, how about for 3 hours?
Also no, because by then, the dough would exceed pretzel's standard mass.
In conclusion, pretzel will have to wait at least 1.91 hours or 1 hour, 54 minutes and 6 seconds, but no more than 2.67 hours or 2 hours, 40 minutes and 2 seconds to achieve the preferred mass of dough from 650 until 950 grams per batch.
She cannot wait for 30 minutes, nor 90 minutes, and nor 3 hours. Perhaps she can wait for 2 hours, which too happens to be the length of our discussion. She can rest her dough, participate and listen, and after the class, create a delicious pastry. Logarithms in baking just makes the process much sweeter. Thank you.